there will be, in that vessel, there will be stresses or forces normal to your surfaces. So if you're going to take this infinitesimal element, there will be a force that's going to bend in one direction and also the other direction. So those basically are normal stresses, and there won't be any shear activities here. So that's a classic example of pure tension only. Yes? And of course, your maximum value or maximum stress will be sigma 1, and the smaller one will be sigma 2. So these are the classical examples that you can have in your notes. Yes? So now we have discussed beam inbending. We applied the principle of, or we applied the, what do you call this one? We applied the state stress concept, and then we determined the sigma 1 and sigma 2. We also looked into a shaft in torsion, wherein we know that it's only a pure shear activity and the normal stresses are 0. And then for thin-walled pressure vessels, which we will be discussing later, it's just a pure normal stresses, or so-called, the only stresses present there are normal stresses. So as you can see, these are 3 major applications of what we did today. Any questions so far? Okay, so you've done the examples. Now let's move on and discuss further. So you have now your stress invariants, I1, I2, and I3. So for this one, I1 is this value, I2 is this one, I3 is this one. So, question. If you want to solve the long method or basically just using this principle, can you do it? Yes. Anyway, you're going to end up with this one anyway. So not a problem. So it depends if you just want to take this determinant and take the roots of your equation, that's not a problem. But if you just want to use this simplified one, which is actually coming from taking the determinant of this one equating to 0, then you can do so. So you can solve your roots of the equation, sigma 1, sigma 2, and sigma 3. There you go. That's the summary there. Now, for example, you only have your principal stresses. For example, you only have your principal stresses and you want to know your invariance. This is how you get it. So again, how do you do that? It's simply taking the roots of the, the determinant of this one minus sigma, this minus sigma, this minus sigma, take the determinant equal to 0, then you end up with this one here. Okay, so not a problem. So let's look into hydrostatic stresses. What are hydrostatic stresses? So again, we're just looking at definitions at the moment. Don't worry, you have a lot of stresses here. You'll have a lot. Elasticity, plasticity, finite element, we will always be talking about stress. Anyway, if it helps, the last year's performance was very, very good, excellent. I think the average of the student was somewhere in the 70s, just a bit to the 70s. So, yeah. So if you want to really take the opportunity to score high in any of your courses, probably take the opportunity to score high here. It's 20 credits, right? Your FYP for 1 year is 30 credits. This is 20 credits. So if you have the opportunity, use it here. So that's the average last year. Well, of course, you are better. I know you're better, so the average must go higher. Must go higher. So I hope that helps. Right, so that relieves a bit of the stress, really, and let's talk more about stresses. Deviatoric stress, later on we will discuss, but before we look at the deviatoric stresses, we have hydrostatic stress. Oh, sorry, by the way, I won't be available. We won't have a class on Thursday, so I'll probably just spread out those 2 meetings that we missed later on. We won't be meeting on Thursday. So, yeah, don't worry, I'll miss you too. So, you can start your homework or your project. Yeah, Thursday only, don't worry. I'll make it up. So here we go. We have the hydrostatic stress. What does this hydrostatic mean? So here you go. Consider this one to be, consider your element, 3D element to be, say, covered by a fluid. Water or whatsoever. And then the stresses acting into this one will be the same. All normals. Okay? So, we call this one hydrostatic stress. I mean, they're all the same. So sigma H here, here, and here are all the same. And they are normal. Acting normal to the surface. So just imagine say a cube that's immersed into water. So it won't change in shape, but it can change in size. Okay, so it can be compressed, depending on the type of material that you use. But what we're looking here is that all the stresses will be the same. So acting on the face perpendicular to X, perpendicular to Y, and of course Z. So all are normal. So if we're going to write this one in a matrix form, your sigma H is simply written in that form, meaning it's just normal. Okay, now imagine your state of stress, 3D, and of course we have this one here. So, okay, so this one is a 3D. So for 2D, what do we have? Let me just change that there. So how do we calculate for this one? To determine this value in 3D, this will be sigma H equal to sigma 11 plus sigma 22 plus sigma 33 divided by 3. And of course, this one is sigma 11 plus sigma 22 divided by 3. How do we, now the challenge here is how do you write this one in initial notation form? So take note, there is a summation. Oh, sorry, this will be good. So how do you write this one in initial notation form? So last time we studied a bit of initial notation. So how do you write this one in initial notation form? If you have a summation, you should have a repeated index, yes? So if it's a repeated index, it's just a dummy index. So we can use any like II, JJ, KK, and so on and so forth, yeah? So this one can be written as, in 3D, this one is sigma. Let's use any variable, so that is KK divided by 3. The same is true with this one. Sigma KK all over 2. So you can have sigma II, sigma JJ, PP, MM, and N, and so on and so forth. These are dummy indices. The reason is that because they are repeated. And if it is repeated, there will be a summation. So here is K equal to 1 to 3. This one is K equal to 1 to 2. So we have now defined a hydrostatic stress, and we were able to determine we were now able to determine its initial notation. So after determining the hydrostatic stress, let's try to determine the deviatory stress. So like I said, we have a lot of stresses here. So after identifying or defining the meaning of a hydrostatic stress, let's define what a hydrostatic stress is. So we have now a deviatory stress. What are we doing at the moment? We're just defining curves. Yes? So you have your state of stress, you have your principal stresses, we have identified hydrostatic stress. Let's have one more. Okay? So let's have a stressful environment. Let's do that. So what do we have for this one here? This one, sorry, Sij is equal to, I'm just going to write the matrix form first. That is your state of stress minus your hydrostatic stress. Yes? And if we're going to write this one in matrix form, this will be sigma 1, 1, right, and this one, so this one is simply sigma h, sigma h, sigma h, and the others are 0. So this is your deviatory stress. So again, you can simply write this one as sigma 1, 1 minus sigma h. So we're just performing some matrix operation at the moment. So that is your deviatory tensor. So how do you write this one in initial notation form? So let's try to write this one in initial notation form, okay? So are you guys with us? Or would you like to take a break? So, how do we write this one in initial notation form? Definitely we'll have the, you'll have your so-called sigma ij because of this presence here. So there's a magic here, so please bear with me. What else do we have here? So this one takes account for this one. So how do we write this one now? So we have now a 1/3 there. So take note, sigma h is equal to 1/3, sigma 1, sigma 2, sigma 3, right? So you can have this one as 1/3 sigma kk. Sorry, 1/3 sigma kk. So let's try to incorporate that here. So to be able to incorporate this one, we need a Kronecker delta. We need a Kronecker delta, meaning that, say for example, if I have this one to be 1/3 sigma kk, right? So meaning that you're adding or you're subtracting sigma kk to all of these terms here. Yeah? So you're adding this sigma h to all of these terms here. If we have sigma ij minus 1/3 sigma kk or sigma h. So meaning we're adding it to all of, or we're subtracting it to all of these terms. So we need a Kronecker delta. So here we simply multiply this one with a Kronecker delta, meaning that if I is equal to j, then you subtract this one. If I is not equal to j, then this whole term will be 0, so you don't have a subtrahend here. So try it. You probably need time to absorb it, but this is how you do it. So sigma h here is present only if I is equal to j. So I is equal to j only 2, 2, 3, 3. So for the others, this value will be 0. So this is the initial notation form of this one. Right? So where are we at the moment? So we have the normal and shear stresses, principal stresses. I forgot to also discuss von Mises stress. We have the hydrostatic stress, and then we have the deviatoric stress. So try to understand them, please. So again, any questions for this one? Try to go home, have a look, try to digest them. We have the normal shear stress, principal, von Mises, hydrostatic, deviatory. So 5 at the moment. questions so far? So what's really challenging is just writing them in initial notation. But once you accept all of this one to be written here, then it's just straightforward. Moving on to learn other skills. Right. We'll continue next meeting. If you don't have any questions, try to digest all of this information that we did. I hope you have questions next meeting. That will be Tuesday. Also, please, you can start now your project. Can I remind you about your project?
Please and next.
Reminder, project, you can download all these things in Moodle. Due date, 6th November. So how do you score high? There will be a lot of criteria there. Try to satisfy all these criteria. It's not just submitting, solving, coming out, everything. You have to answer all of the questions and then have to present it in a meaningful way. Plagiarism, there was a case last year. So I think the student was very bold to really copy and revise. But of course, Turnitin can always see into this ones. So of course, it went to the Senate, and the Senate decided that the person who copied will get 0. And then the person who had his project copied was also deducted 2 points or two marks. Not 2 points, 2 marks. So instead of having like A5, so he was able to get 2 marks, is B1, B2. So even though it's 20%, it can make a difference, right? It can make a difference. So as much as possible, you're allowed to collaborate, but you're not allowed to copy. Due date will be on the 6th of November, so you can start your projects as early as possible. Any questions for this one? So how do you submit? It's the same with the submission for Mechanics 3. So 6th of November, I will be just having a Dropbox there outside of the office. Just drop it there. So not a problem. Shall you only submit hard copy? No, submit hard copy and soft copy, because the soft copy I have to look into, or we have to use Turnitin. One hard copy, one soft copy. Any more? Is it possible to get 20 marks? Yes, it's possible, not a problem. Is it possible to get 0 marks? Yes. I've already explained that already, how you can get 0 marks. So between 10 and 0, I'd rather get 10 rather than 0, right? So, any more? Peer-wise, 5%. So what's the worst thing that can happen? If you're going to make a mess out of this work, at least have 10 per project. You have what? 20 plus 5, 25. So how many more do you need for the exams to be able to pass? So you need 15. So that's just okay if you want to pass, but a lot of students have been really taking the opportunity last year to score high here, so I hope you'll do it too. Right? So any questions? No questions? I hope I can have some questions next meeting. You can go. Thank you very much.